Welcome everyone to our DSRC security seminar series. And I'm really very pleased to have our speaker, Professor Konrad Rieck, who is a professor at Braunschweig University, TU Braunschweig in Germany. And I would say that he's one of the few researchers or early researchers who started working on machine learning and security, and he has been super consistent, like years of history in that direction. And it's really very nice. And I still remember first time when I met him in Berlin. It was a conference, EC2ND, I think, and it was like, okay, super nice to meet him at the time. And then since then, yeah, sometime we just exchanged messages. I was in France at that time, and I visited because I had a paper, and I am pretty sure there was something with that paper also. and then he has actually had some interesting, I would say, research that is really, I would say, pioneering in the community. For example, we have code property graph, which is definitely one of the vulnerability extrapolation, which is like somehow related to that. So, and then today he will talk about image scaling attacks in machine learning. So this is something which we have been actually seeing a lot nowadays, and somehow, let's say, adversarial machine learning part, where people are relying a lot on machine learning capability of understanding something and how good or bad it is. So I would now let Konrad to take the screen and share his thought.
Yeah, thanks a lot. Thanks a lot for the invitation and the very nice words. Long ago that we met in Berlin. I also remember this because I was so crazy to organize a conference as a postdoc. And I was very happy when it was over because it was a lot of pressure and responsibility. Yeah. Okay, but anyway, that's a completely different story. So today I want to talk about image scaling attacks, and this is a class of attacks that affect machine learning systems. So I'm not talking about software security or code property graphs, but something that is really part of many machine learning systems. Let's check my pointer here. So, and I start with this picture, which shows a very simple overview of how machine learning systems typically look like. It's more an overview. It's not like the technical detail of an algorithm. Let's look at this picture. So on the top, you see you have some data in the training phase. You have some labels, and then this goes into a learning algorithm. The learning algorithm will generate something like a learning model. This can be a neural network. This can also be a set of support vectors or a random forest. And on the bottom, you can see the so-called application or inference phase. And in this phase, novel data comes to the model, and then you make a prediction based on the model. So far, so good. This is somehow at the very core of all of this great, glorious machine learning, artificial intelligence hype. And it's super cool in short words. But I guess you also notice that there's these needles in the learning algorithms and in the inference phase. And these needles correspond to the recent hype around adversarial machine learning. There have been thousands of papers on attacking machine learning in the last years. Nicolas Calini, a researcher from Google, he's tracking these papers. And I think his database already covers 3,000 papers talking about attacks against machine learning. Now, I could also talk about this, and then this would be this 3001 paper on attacking the learning and attacking the inference. But there's something that all of these papers, or most of these papers, omit because it's boring. And machine learning systems do not look like I show, but instead they look more like this. So before you can work with the data that you have, you almost always perform preprocessing. This preprocessing can be a normalization of the data. It can be a parsing of code, for example. In computer vision, very often you have to scale images, and also very often you do some form of feature extraction before you apply the learning algorithm. And in the application phase, you do the same things before you do the inference or before you compute the predictions. And people consider these steps to be boring because they are pre-processing. I mean, already the name indicates pre-processing. That's something that you do before the real cool stuff happens. Now, from the security perspective, however, things are a little bit different. Security researchers need to look at all steps that happen in a system. And what we did in other researchers is we looked at pre-processing in machine learning systems. And in particular, this talk is about image scaling, which is a very common, omnipresent, very simple, popular step in all computer vision systems. And this talk is basically designed in 3 parts. And in the first part, I will talk about this new attack. It's 2 years old, and it's called image scaling attacks. And of course, what I present to you is not my own work, but the work of my group and other people. And most importantly, it's work by Erwin Quiring, who's the author of our main paper and also other papers related to image scaling attacks. So if there's some nice things in the talk, very likely Erwin has engineered or built or designed them. Okay, so let's talk about these attacks. And to do this, I need to jump a little bit into the past. In 2019, so roughly 2 years ago, a paper popped up at the Usenik Security Symposium, and this paper introduced a variant of adversarial examples. So something that looked very similar to what we have seen before. And when I was reading the paper for the first time, I thought like, okay, this is well-known things. The only thing that was a little bit strange is that somehow in the attack, there was a scaling algorithm. And the authors presented an optimization problem and said, like, this is a new form of attack. And in this attack, we work against a scaling algorithm. And I show this optimization problem here to you. And let's look a little bit at it to understand what's going on. We don't need to know all of the mathematical details. It's just quite a simple thing. So we start at the bottom. Can you see my mouse pointer? I assume you can. Oh, wait, can you see it?
Yes, I can see.
Yes, okay. So at the bottom, you can see there's an image S, and something is added to this image. And then the image and this added thing is scaled, and something is subtracted. And this subtracted thing is called the target. And we want this whole thing to be smaller than some epsilon. So but in principle, this says that we add something to our image and we scale it, and then it should be very similar to a target image. And on the top, we can see a minimization. And this minimization essentially says that whatever we add to our image, it should be very small. So we want to add some small noise, some small changes to the image, and this should somehow manipulate the scaling. Yeah, and when I saw the paper and talked with my team about it, we were not really impressed. So we said, like, this is, I don't know, it looks strange and it feels strange and maybe it's not good. So what we did is we generated or reproduced this attack. We implemented this optimization problem and then generated our own examples. And here's one of the examples that we generated. And I must say that I was really amazed when I saw it for the first time. So what you can see on the left is an image of a cat. This is our S. And on this image, added to this image, there's a very fine level of noise perturbation. And if this image is scaled to a smaller size, it changes to become this dog. So there's no post-processing or manipulation here. This is really happening exactly as shown on the slide. And if you look very closely into the image of the cat, so I magnified a region, you can see dark dots in the image, and these dark dots are this added noise to the image. And I found this really amazing, that by adding this very small, subtle noise to the image, the scaling operation seems to do something completely different and returns an image that is not visible in the original larger version. We can also do this with other images. So here's another example. You can see two cities. And again, if you look very closely, for example, into the sky of the big image, you can see there is a fine grid pattern in the sky, but you would never suspect that this grid pattern manipulates the scaling and changes the output to a completely different image. So when we did this, we were really amazed, and we had to say kudos to the authors of this paper, because it seems that this is a very powerful and yet unknown attack. And we thought, like, okay, but what's the impact? Can this have an impact on learning-based systems? And we thought about possible attack scenarios. And when we did this, we found out that in principle, this is a very versatile attack. In fact, the attacker does not need to know anything about the learning model. So it doesn't matter whether you're using a neural network, a convolution, a neural network, or some other learning algorithm. Or it might even be that you don't use any of these algorithms, but classic computer vision techniques like segmentation and things like that. Because the attack changes the output of the scaling, and from this point, the attacker has full control of every pixel. So this means the attacker can freely choose the output of the scaling, and then everything that happens afterwards is already under the control of the attacker. The only thing that the attacker needs to know is what scaling algorithm is used and what is the output size. So he or she needs to know this. Now, in many settings, the scaling algorithm and also the output size of the scaling are no secrets. Very often this is well known. So for example, if you take these freely available large neural networks like VGG16 or other networks published, it's clear what kind of output size that the scaling needs to produce, and also the scaling algorithms. There are not so many scaling algorithms available. And you can do pretty strange things with this attack. So I have sketched for you two examples. So on the left, you can see a poisoning attack. So what I did here is I manipulated an image, but I did not manipulate the complete image, but just a part of it. So the large image shows a traffic sign that says speed limit is 40. And if it gets scaled, the 4 changes to a 1. And this means that if you have this data point in a training set, a human will look at it and say, okay, it's a traffic sign with 40 on it. But if it gets scaled and then the learning algorithm works on it, the learning algorithm will see the 10. And therefore, the learning algorithm will associate a speed limit 40 with an actual image of a 10. So the car later might not do the right thing when it sees the traffic sign, but instead drive with a speed of 40 miles per hour. That's a poisoning attack because it happens at the training phase. Now, we can also do this attack on the application phase. So what you can see here is a photo of myself. It's a typical German biometric photo. So you have to look straight into the camera, and this then becomes a passport photo. If I would hand this in as a digital version to the German administration, and they would then use this in a face recognition system, they had to scale the image. And if they scale it, it becomes a different picture. So with this attack, it would be possible for an attacker to hide a face recognition, because the original supplied photo that is used for analyzing the face is different when it is scaled. So this means the attack affects both the training and the application of machine learning. And this creates some very dangerous situations. So the next thing that we then thought was, okay, maybe this is an interesting, versatile attack, but what about the scaling algorithms? I mean, I haven't talked about details yet, so it does affect all algorithms or some. And what we did is we analyzed major machine learning frameworks like TensorFlow or PyTorch and CaFi, and we checked the scaling algorithms in these frameworks. And we tested whether the attack works against the algorithms. And what you can see in the table here is whenever there's a red mark, then the attack is vulnerable. The scaling algorithm is vulnerable. And if you see a green cross, the algorithm is not vulnerable. And the picture is inconsistent. So we can see for some frameworks, let's say TensorFlow, for example, some algorithms are vulnerable, others are not. We can see that for other frameworks, there are also vulnerable algorithms, but not the same. So for example, in PyTorch, bicubic scaling is not vulnerable. For TensorFlow, it is vulnerable. And so it's unclear what's going on here. But what is clear is that if we look at the default setup marked by a star, in most cases, the default scaling algorithms are vulnerable. So we have a problem, and the problem affects the default setting. So it looks like a real security problem, but we do not really understand what's going on. And this motivated us. I mean, there was the paper from other authors that introduced the attack, but they could not explain what's happening. And they could not really explain, let me go back. They could not really explain why sometimes there was a vulnerability and sometimes there was not. And some algorithms seem to be affected always, like nearest scaling, and other algorithms like bicubic or Lanczos scaling, they are affected sometimes, but not always. So we were really confused. And the original paper said something about neural networks and the complexity of learning and blah, blah, blah. But the truth is here, we're not talking about learning algorithms at all. All that we have at our hands are scaling algorithms. And scaling algorithms are something very simple. I thought they were super simple, super easy to understand. I must admit, we have never looked before at scaling algorithms because they are so boring and just simple preprocessing steps. So something needs to happen in the scaling process that has a security implication and that allows this attack to work. So what we did is I asked two of the members from my team to take a look at the implementations and really go into the C code of TensorFlow, of PyTorch, or CaFi, work through the code, and really get an understanding of what is happening in these implementations. And this is what we did. And we found out several, I would say, interesting things. Maybe if some of you come from the field of computer vision, these things are not surprising, so you know them. But for somebody like me, who comes from a security background, I found this surprising. So the first thing that they found is that the algorithms all do not work on the complete image, but instead they first scale the image horizontally and then vertically, or the other way around. So the scaling is not a two-dimensional operation, as I would have thought. It's a one-dimensional operation. Yeah, so it's essentially it's a one-dimensional signal. Let's say a row of the image, and this row is scaled to a smaller row. And this means for us, when we do this analysis, we can restrict ourselves to one-dimensional signals. So we can look at these rows, or we can look at these columns that are changed, but we do not need to think about a 2D object anymore. That's good. And the next thing that we found is that in all of the cases, there were pre-computed weights, and these weights were used to somehow aggregate multiple pixels to the scale pixel. And I guess this was already clear to me that scaling has to do with kind of bringing multiple pixels to a few pixels And this is done with some magic weighting. And this weighting essentially defines the type of the scaling algorithm. We look closer at this and how this weighting works. And we found that you can describe it as something that is called a convolution. So these weights actually define what is often called a convolution kernel. Not to be confused with the kernel in machine learning. So it's a function that takes a window of pixels, computes an aggregate of this using some predefined weights. And this is run over the whole signal, so over the column or over the column or the row. And this enables the algorithm to shrink the pixels into the scaled version. This can be written in this typical convolution form here, which is an infinite sum, but it's easier to see if we look at the weights that define these convolutional kernels. And here I show you three possible weight functions that are moved over this window. So if this is a very peaky function, then we have so-called nearest scaling. This means only a few pixels in the very middle are important, the rest is ignored. If we have bilinear scaling, the kernel weights have a linear shape. If we have bicubic scaling, this kernel window has a cubic shape. So essentially, we can describe all of the available scaling algorithms using this concept of a kernel that has a certain width and certain weights on this width window of a width. Yeah. Okay. So does that help anybody? Where's the problem? And when we talked about this with people that know a lot about signal processing, they made some remarks. And let me show you these remarks. So they said, well, what you describe, the process of reducing a one-dimensional signal and making it smaller, is well known in signal processing. And also using a convolution filter or convolution kernel for this process is also well known in signal processing. And this is called downsampling. It's a little bit like reducing the sampling rate of some signal. And the only thing that doesn't fit in your description is that there's no low-pass filter. And we, at the first time we heard about this, we did not understand what was going on. But they explained to us that if you do downsampling of data, you can get these aliasing effects in the images, but also in other signals. So for example, if you downsample audio, you can get some kind of noise in the audio. If you downsample an image, you can get artifacts in the image like small pixel that are not nice to have. And to avoid this, it's common practice in signal processing to do a low-pass filter, which means you're reducing high frequencies in the original signal, and then you do the downsampling process. Now, in the scaling algorithms, we could not find any low-pass filter or something related. So instead, the data is taken as it is and then transferred to the smaller version. And this means aliasing effects can exist, and even worse, the attacker can use these effects to his or her intention and make use of these effects to create new content in the image. And this can even be further simplified in a very simple sentence. And this is most of the pixels in the original image do not really matter in the convolution. And we made this more precise by analyzing how exactly the individual pixels contribute to the scaling. And you can see this here in the example on the bottom. So I'm now talking of a signal S, but you can assume that this is also simply a row of pixels in an image. And these lines in this signal correspond to the color, or let's say the brightness of a pixel. So large line is a very bright pixel, dark line, small line is a dark pixel. And what we can see here is a scaling with a bilinear kernel function. So we have this bilinear shape. And the signal is scaled to a smaller version that has only 2 pixels. And what's interesting here is, how do the different pixels contribute to the scaling? And the first thing that you should notice is that there are several pixels that do not contribute at all to the scaling. So I count 1, 2, 3, 4, here. This pixel, this pixel, this pixel, this pixel, this pixel, this pixel. So 1, 2, 3, 4, 5, 6 pixels have no influence on the output. So an attacker can ignore them because they don't matter. They create the image for the viewer, but they are irrelevant for scaling. And when it comes to the scaling, only 3 pixels contribute, which are these 2 and this one. And also the contribution differs. So here, this pixel alone defines what is happening. And here, the mixture of the 2 pixels defines what's going on. And this can then, so this is the abstract description, but we can make this very concrete. We can say essentially the size of the kernel function matters, or the width. So this is how wide this area is here. And the shape of the kernel function matters. This is whether this is a linear function or a bicubic function. And of course, the scaling ratio matters. So are we scaling from like 10 pixels to 2, or are we scaling from 10 pixels to 4, or maybe to just 1? And I'm not presenting all the details here, but we could show that the scaling ratio, the shape of the kernel function, and the shape of the width of the kernel function are the dominant factors that decide whether this attack is effective or not. To show you one example, we did experiments for all of these factors and checked how they influence the success of the attacks. And to describe this experiment, what we did is we took 600 image pairs, and one of these images in each pair was the source image, one was the target. They were randomly chosen. And then we had a neural network, VGG19, as our victim, and we scaled the images and we tried to conduct the attack on these image pairs. And to check whether there's really something happening, we had a user study. So we asked 36 people to look at the images that have been manipulated by the attack. This is necessary because the attack in principle can also change the source image and make it look like the target. And in this case, it would not be an attack anymore. So what matters for image scaling attacks is that the original version looks unsuspicious to a human, and when scaled down, changes its appearance. So you need to have a human to look at the source to see whether the attack really works. And what you can see on the bottom is a part of this experiment. It was a larger one. And we asked the participants, do you see something suspicious in the image, in the original manipulated image? Do you see that there is an attack going on? And if the bar is green, then the people could see something, and they reported, there's something fishy. But if it is red, sorry, if it is red, they could not see anything. So in this case, they said this is a totally normal image, although it was manipulated. And what I'm showing you here is 3 different scaling algorithms, and what we changed was the scaling ratio. We left all the other factors, such as the kernel width, to the same size. And you can see that for a scaling ratio of 2, most of the attacks had visible artifacts, so people could see something. But once we reach a level of 4 or 5, the attack becomes more and more effective. And for example, for 5, the majority of the manipulated images is not detected anymore. And if we turn to a scaling ratio of 10, which of course is a very large ratio, none of the attacks is visible anymore. So I see there's a question. Oh, it's a long question, yeah. But let me have a look. Okay, that's something that I need to think about. yeah, the question here is the scalar. So the question is whether the scaling algorithms can be are differentiable, and if they would be differentiable, you could go backwards, like in a neural network, and then you could essentially explain what features contribute. We didn't do this. I'm also not sure whether these algorithms are differentiable. I think some of them are definitely b-cubic or so. I would expect to be differentiable. For nearest scaling, I'm not so sure because it's just one peak. But in any case, we didn't need to do this step, but instead we did it, let's say, on the manual way by just analyzing the algorithm with human brains. So we could definitely identify those pixels that contribute based on scaling ratio, kernel function, and kernel width. But this is an interesting idea. So potentially it would also have been possible to do this automatically at the price of not understanding what's going on, but still finding out what pixels contribute and what pixels do not contribute. Okay, so at this point, we essentially finished an analysis of the attack, and we had a good understanding of what's going on in the attack. And that's something that does not happen so often in adversarial machine learning, that you really have a good understanding of what the attack is doing. For example, if we look at adversarial examples, so adversarial inputs to a learning algorithm, very often it is clear how the attack is constructed, but it's not clear why the attack works. What's the reason? There's some theories about whether this is some features of neural networks or whether this is some related to overfitting and things like that. But in our case, we could really pinpoint the success of the attacks to these three factors. And of course, we could now play with these three factors. And this is what we did. So we started, okay, if we know what's going on, maybe we can define a defense that provably works. And it started with something that I would call the democracy of pixels. Yeah. So we all want democracies. So if scaling should be democratic, then every pixel has to contribute to the scaling process. It's not okay if we leave some pixels out, if we ignore them. And every pixel should have the same weight, should have the same right in this democracy. So we thought about this, and essentially this implies that we need to design the kernel window and the kernel shape such that this property holds. So we cannot influence the scaling ratio because the scaling ratio is defined by the operator, the user. The user says, I want to scale it from this to that. But we can then adapt the kernel width and the kernel shape such that every pixel contributes and every pixel has a uniform weight. And we defined what we called a robust scaling algorithm. And we were very proud. So for a day or so. And we said, okay, we take the scaling ratio as the input, and then we define the kernel width such that every pixel is covered. And we define a flat kernel function, a flat convolution, where everything has exactly the same weight, and that's it. And then we were proud and said, like, okay, maybe we will be remembered in the past as the researchers that invented a new scaling algorithm that is robust. Now, unfortunately, it didn't take too long until we found out that, of course, this scaling algorithm exists. It's not new. It is called area scaling or area interpolation. And it's part of every framework. So if I would go back to the table, you would see it. It's at the bottom of the row. It's implemented in all of the frameworks. However, mostly it's at the very last place in the list. So people don't like this algorithm because it's slow. Of course, every pixel is considered. So it takes the whole image. There's no shortcut. And it's a little bit blurry because all of the pixels contribute exactly with the same size, same input. But still we said, okay, maybe we didn't invent this algorithm, but still we can do an experiment and see whether it works as a defense. From a theory perspective, it has to work. So we did an experiment that was identical to what we have done before, but this time we used area scaling. And surprisingly, or not surprisingly, the defense worked very, very well. So for our 600 image pairs, none of the attacks was successful anymore. So you can see an example here. So you can see on the left a scaled image with nearest scaling. The image shows a cat, which is not on the original image. And on the right, you can see area scaling. And here the original image is shown, which is an espresso or something. However, if you look very closely, you can still see the cat somehow in the scaled version. This is because area scaling treats all pixels in the same way. So a little bit, this grid pattern is also part of the resulting image, but it's reduced a lot. And machine learning algorithms do not recognize here the cat anymore, but see the true image. So bottom line, area scaling is a robust scaling algorithm. It's available in all the libraries, so you can use it right away. The only downside is it is a little bit slower and it's a little bit blurry. Okay, so we were now a little bit frustrated because we did not invent a new algorithm. So we said, okay, let's try to at least invent something new. And the idea came up that maybe if we know so much about the attack, know so much about the pixels, maybe we can just remove the attack. And this would have the advantage that later then we can use all scaling algorithms, and essentially the images are now safe or secure. We thought about this and designed an attack that tries to reconstruct pixels that are, or remove pixels that are vulnerable and then replace them with something safe. And to do this, we again followed our design principle, which state every pixel should contribute in the same way, and every pixel should have the same weight. So, but instead of doing this at the scaling, we do this in advanced, and we do this kind of reconstruction only for those pixels that are affected by a given scaling algorithm. So if we know the scaling algorithm, we know the input size, we know the output size, we can precisely identify the vulnerable pixels. We could also do this with the gradient, by the way, if this would be a differentiable algorithm. So in this case now, we have this image on the right, and the red pixels, those correspond to vulnerable pixels. It's not clear that there's an attack, but if there would be an attack, the attack would target these pixels. So what we do is we remove these and we replace them with something else. And our idea is super simple. We take a window around the pixels. The window is exactly as large as needed, such that every pixel is considered. And in the window, we have two options. We can use the median of the color values. So this would be a reconstruction based on the median of the window. Or even simpler, we could just randomly pick one of the pixels from the window and put it at this position. And we call these defenses a median and the random filter because they're very, very similar to what is typically done in computer vision and also called median or random filter. So again, there's actually not a real invention here, but we use the concept of a median and the random filter to reconstruct the pixels that could contain the attack. So we again evaluated this. You can see left, no defense, and you can see then on the right and in the middle, the median filter and the random filter on the image. And the median filter creates a perfect image. There's no artifact of the cat anymore. The random filter also completely removes the attack. So you cannot see anything from the cat, but you also notice it's a little bit noisy because of the design. This is a random replacement of pixels. So there's a little bit of fuzziness in the image. We repeated our experiment again with the 600 images, and in all 600 cases, the attack was prevented with one of these two filters. So this means we have a working defense that you can use if you do not want to use area scaling. So if you want to use nearest scaling or bilinear scaling, you can use these filters, and then you are on the safe side. There's, of course, also a drawback. Nothing comes for free. The median filter induces a little bit of overhead. And the reason is that you need to compute the median for each of the pixels that are vulnerable. So we know from our computer science courses that the median can be computed efficiently in linear time. But it turns out that this doesn't really matter in an implementation as simple as this. So even if we use these fancy median algorithms, we have a measurable overhead. It takes some milliseconds longer than usual to scale the image. On the other hand, there is the random filter. It has almost no overhead because it just randomly picks the image and puts it somewhere. So the runtime is mainly dominated by finding the vulnerable pixels. This is just a very simple arithmetic computation. So it's super fast, but it creates this noise on the image. So depending on what you want to do, if you want to have a high performance system, random filter might be a good choice. If you want to have a rather precise system, the median filter is the better solution. Okay, at this point we were, let's say, almost done, but we know our communities, the security community. And the security community, the first thing that they will do if there's a new defense is it will be attacked. And what you do as a researcher to be a little bit more safe is to attack your defense yourself and try to find out whether something is possible, whether you can evade it. So what we did, I'm jumping, this is an example of the median filter, but what you can see here is how the median filter really removes the grid introduced by the attack. No, but let's talk about the robustness of our defenses. So what we did is we integrated our filters and also the area scaling into the original optimization problem. So instead of just having a scaling algorithm in the optimization problem of the attack, we integrated our filters. And then we let run the attacks again. So this is a scenario where the attacker knows precisely that we have a defense in place, and the attacker also knows precisely how our attack works. This is called an adaptive adversary. So he or she is very well aware of what is happening on the side of the defender. And now he or she is adapting the attack to this new scenario. But fortunately, we found out that you can plug all of this in the optimization problem, but the generated images will not look that good anymore. So let's first look at an image. So here on the right, you can see an image that this new attack creates. And it's a mixture of the source image, which is a dog, and what is this, a grasshopper or something. And it's not possible anymore to hide this added noise on the image. It becomes visible. And there's also a reason, and you can even prove this. We did this in our paper. The reason is that the attacker now needs to control and change more pixels of the image. So for example, we look at area scaling. The attacker needs to manipulate the average of a window of pixels. And controlling the average means that you need to change a lot of pixels. You cannot arbitrarily increase or decrease the pixels. They are bounded. And therefore, in most of the cases, we found that on average, 50% of the pixels need to be changed to make the attack effective. The same holds for the median filter. To control the median of a window of pixels, again, you have to change on average 50% of the pixels, which creates visible things. And also for the random filter, the same holds. To control a random selected pixel, you actually have to control most of the pixels in the window. Otherwise, your pixel will not be selected. And this means that from our analysis, from this analysis, our defense is not broken, or maybe cannot even broken, and new ideas are needed. And of course, there are new ideas already. I saw a paper already that is attacking our approach, but it changes the threat a little bit. So I don't have slides on this, but of course you can say the scaling is secure, but still, what if we don't want to change the image completely? But what if we just want to change the image such that the machine learning algorithm misclassifies the image? So in this case, fewer changes are necessary. However, the attacker is now not only attacking a scaling algorithm, but also a learning method. So it's a combination of both, and we lose this agnostic approach. So we cannot attack any method. Now we need to know the learning method at the end. But in this case, it is possible to make fewer changes, because now we don't want to trick the human anymore. We want, or any method, but we just want to trick a particular neural network. There are also other ideas that people come up with. There's no paper to my knowledge, but of course, things become easier if the images already look very similar from the start. So if the images are almost the same, it might be that the attacker does not need to change 50%, but less. And then, of course, the attack becomes less visible. Okay, so this brings me to the end. I think that's already enough content for a talk, so that we can also maybe talk a little bit about it and discuss things. I have two slides for the summary. One is kind of the typical summary, but there's also a little bit more that I will show you on the next slide. So what's the summary of the image scaling attacks that I presented? So the bad news is there's a new family of attacks against computer vision systems, and those attacks affect the scaling part. And they can have an impact on training and the application of machine learning. And I would unfortunately expect that maybe also other preprocessing steps in computer vision are vulnerable, not to this particular attack, but to related attacks. So when you are a computer vision person or researcher, you need to watch out for preprocessing. In our case, we have developed defenses. Area scaling is already available, so there's no reason to have this vulnerability in your system. We have set up a website where you can also download our implementations of the median and random filter. We have also submitted a patch to TensorFlow. There's also a change in TensorFlow. I'm not sure whether we initiated this. I don't think so, but there's also a change in how scaling is configured. You can now decide whether the kernel width is adapted to the scaling ratio, which is very close to what we also found out. So it seems like this is moving forward. And if you want to use scaling, I highly recommend to watch out for these simple defenses. And then I promised something that is maybe beyond this talk, but also interesting from a very general perspective. So what we see in the attack, or what is at the core of the attack, is that we have an image and the machine sees a different image than the human. And this can be formalized, and we could say there's a disagreeing view on the same data. I mean, the data is the image. The human sees the original version, the machine sees the scaled version, so the disagreeing view on the same data. And this is a pattern or a vulnerability class that actually happens in several different variations already. And people already write papers on it, but they don't notice that they are actually working on a general theme, which are attacks against preprocessing. So for example, there's a recent paper on homoglyph attacks on texts. I'm not sure if you have heard about this, but there exist alphabets in which certain characters look very similar to characters in other alphabets. So for example, there is a special A in Swedish, I think. Actually, I don't know it, but I think so. There's a German umlaute, which is Ö and Ä, which look like O, A, and U. And for many languages, there exist these homoglyph characters that are very similar. And sometimes you can see it. Sometimes these differences are very, very small. So for example, I think in the Hungarian language, there is an I that doesn't have a dot on the top. So for a human, it becomes difficult to differentiate whether you can see this I or whether the I has a dot on the top. Plus, modern Unicode also allows to move and delete while writing text. So for example, you can switch the writing order of characters. This is to support Arabic languages, but you can switch multiple times. So you can write a word in reverse in the text, and before the word comes, you switch the reading order, then it is written in the opposite order, and then you switch back. And these attacks essentially do the following. The text for a human looks perfectly okay, and for the machine, it looks completely different. And this is similar to scaling attacks on a completely different domain and also completely different technical basis. The same can be done for sound. I guess you all know MP3. MP3 is a psychoacoustic compression. So this means the compression removes those things that humans cannot hear. And if this part contains an attack, the human cannot hear the attack, but the machine can hear the attack because the machine typically does not apply psychoacoustic filtering before processing audio. So again, disagreeing view on the same data. And last, maybe, I'm not sure whether you are working with malicious software, but it could also be that even machines have a disagreeing view on the same data. And very often we observe this in malware research, where there's a malicious program and the virus scanner, for some reason, fails to see the malicious code because it maybe parses the file a little bit different, or maybe the file is also polyglot, which means it can be seen as different formats. So it looks like an executable file, but at the same time, it also looks like a zip archive. And depending on what type of file you consider, your analysis then differs. And this also leads to these kind of vulnerabilities that are, I would say, all rooted in vulnerable preprocessing. So the bottom line is we should make more of these needles and put them into the preprocessing instead of just the machine learning. So that's it. Thanks for listening. And if you have questions, I'm looking forward to your questions.
Thank you, Konrad. It was really a very, very interesting talk. In fact, honestly, I was like during your talk, I was really thinking, oh, wow, oh, this is nice. But unfortunately, this in online mode, such expressions do not reach to the speaker. I mean, that's why, I mean, yeah, definitely, it's really very nice. Okay, so now we are open to questions, and either you can ask question directly because I don't see that there will be problem, or you can write question if you want, and you can raise hand also. And while you are thinking, if you want, if the question that you want to ask, maybe I can ask one quick question to Konrad. So this is a nice thing because when you started investigating, you went in the code. Also, like, okay, in the code you started looking at this. Okay, fine, the scaling is done in from the code perspective in a single dimension, first this dimension and other dimension. So I was just wondering now, like, and also it is all about preprocessing. It means that your machine does a lot of things. So is it also possible, like we change image such that it's not about, like, let's say fooling the machine learning vision part or understanding of the image itself, but rather than, let's say, it is more or less towards the machine processing, like it is really now doing a lot of processing, kind of like. So this could be also a problematic thing in certain scenarios, because either real-time systems or constraints are there, things like that. So have you observed anything like that?
Yeah, so I mean, it's I would say a little bit related, but yeah, we tried, or we worked, or we still work on attacking PDF documents, and the goal is that not only the machine but also the human is fooled depending on what we want. So the PDF looks different depending on what we want to do, and these attacks are they are purely technical. So they exploit vulnerabilities or confusion in the parsing. So this is unrelated to machine learning, and it's classic. It's classic software security to look for these confusions. It's not like a crash or something that you can find, but there's also this field of differential testing, where you have, for example, you have multiple programs. They, I don't know, pass SSL certificates, and you just then fuzz the SSL certificates as an example, and see whether they still agree on the fast certificates. And if you reach a point where they don't agree, you have found, a vulnerability. It's not a crash or something, but it's a disagreement. So you know that one of the, and this is, I would say, a variant of what I've been showing, and also something that we look at.
And we have seen that your code is available for all this analysis.
Yeah, it's available. So in principle, you can also run all of these attacks. Also, we don't only have the defense, we also have the attack code. So the example that I showed, I generated them myself. So it's foolproof. So even the professor can run it. So it's not like it's not a research prototype. And it's of course fun to do this. And I mean, it's if you want to, you can play around.
So one final question from my side, like when we started all these things, like, okay, it was really nice that, okay, the attacks means the resulting images were definitely totally different. So from the attacking perspective, how much we could actually control, like what we want to do with this image? Kind of like, is it like dependent on the image, or we have a lot of flexibility there that, okay, we can do a lot actually from the attacker's perspective?
Yeah, from the perspective of the attacker, you can look at these three factors that we identified: scaling ratio, kernel function, kernel width. And depending on these factors, these factors decide how much you can do. And let's say you scaling an image by a factor of 10, which is a lot, then you can control really every pixel of the output, 100%. And it's not visible anymore. And the rest, of course, then there's a smooth transition from all of these parameters to the very end, where let's say you scale the image by 1.1 or so. So you scale it only very little bit, and then of course it doesn't work anymore, because you cannot hide the changes, because now every pixel is considered, every pixel has a similar weight, because the output is very similar to the input. Yeah. And another interesting question, so maybe I can ask myself the question, of course, is what you can also do with this, except from machine learning, because we have thought about this for a long time, and we still don't know. But what could be interesting is social media, because if you post something on Facebook or Twitter, typically the image is also scaled. And also, if you receive messages with WhatsApp or with other messengers, also you see a scaled version of the image that is transferred. We have a student working on this, and it's not clear, but there's also definitely the chance of having a disagreeing view. So it could be that you get an image from me, it shows something, and when you later look at the original image, it's something else. I'm not sure what I could do with this, but I have the feeling that I can do very evil things with this.
I can sense it, and exactly that's the scenario. Oh wow, that is really problematic. Like I mean, of course, definitely we can see a lot bad thing, actually, not good thing.
No, that's no good thing with it.
No, it's definitely a bad thing. Okay. Well, if there are no more questions from other participants, then I would definitely end the seminar with a big thanks to Konrad, and definitely TII, me personally, will remain thankful for your time that you agreed to give this seminar, and maybe we will sometime try to have you again, maybe on site sort of thing, if it is possible. It will be great. It will be great to have you here actually.
Yeah, in the far future.
Yes, far future. Yes, exactly. Okay.
Yes.
So yeah. So thank you, Konrad, for your time. It was really great having you here for a very interesting talk.